Good afternoon. Are you able to get me, everyone?
Yes, sir. Good afternoon.
Yes. Okay, so let me see what I can do so that I try to share my screen with you. Those that are finding problems with audio, they'll be able to solve it themselves. Okay. You can see my screen, right?
Yes.
Okay. So I'm going to continue where we had left off. If I think we remember very well, we were looking at the down sell. Okay. And so under the down sell, I think we discussed why it is important to produce to obtain solid sodium from molten sodium chloride. And I think I did explain to you about the reactivity series. Okay. And this reactivity series, I think I used this this acronym where I said you have potassium, you have sodium. Okay, so it was going like poisonous sausages. Can make all Zambians ill, if you remember very well. Then lead, hydrogen somewhere there, then copper, then we had silver and gold. Okay, and so this was the reactivity series, and some of you were asking me, why is it that it is, if we were going to use aqueous sodium chloride, okay, if we're going to use aqueous sodium chloride, we know that in aqueous sodium chloride we're going to have hydrogen ions, and we're going to have hydroxide ions. So if you can see on this downs cell, that this part is positive and this part is negative. Okay, but there's this separation which makes sure that the sodium solid and the gas are not interacting. Are we together? And so we saw that the path of the molten or the liquid sodium was passing through this direction, coming downwards like that. And the chlorine gas was moving this direction. Now, those of you whose mics are on, please try to switch them off. You are disturbing our lecture. Okay. Just try to switch off your mic, please, because when you're speaking, everybody can hear you and you're just disturbing our friends. I hope everybody can get me clearly. Okay. And so using this clear diagram, I hope everybody can see clearly, right? Are we all able to see clearly?
Yes, sir. Yes.
Okay. Okay, perfect. So I should also mention to you that I am recording this lecture. So when I'm done, I'm going to post this lecture for you, just like the way I'll give you those recorded video lectures. This one is different because all of you are participating. So in the recording, you will be there. Okay. There's a question. Somebody's asking a question. Yeah, okay, fine. You're responding. Okay, fine. So I think I did explain in detail on this one. Okay. I think I did explain in detail on this one. However, we stopped our lecture, I think, here where we were looking at some of the most important reactions for alkali metals. And we said that for alkali metals, we know how the reactivity is. It increases going down the group. Okay, so you have lithium, okay, you have sodium, potassium, and coming downwards. And all of us, I think, reached a point where we said that francium, okay, because reactivity increases going down like this. The last one is francium here. So this one is the one on top and this one is the one at the bottom. So the most reactive is actually francium, but on this line, it's cesium. So we'll say most reactive. Then this one is going to be the least reactive. Now, those which are least reactive, remember, I want you to know that we are saying that if we are comparing the group 1 metals amongst themselves, then lithium coming downwards, that's how the reactivity increases. But if we're going to compare these metals with other metals, the group 1 metals are very reactive. I don't know whether you have gotten that point. So if you're going to compare group 1 and group 2, all the group 1 metals are more reactive than the group 2 and the transition metals. But if you're going to compare them amongst themselves, then reactivity increases going downwards because due to those factors, I think that I did mention to you, if you remember very well. Okay, so here we can see that lithium can easily react with just atmospheric oxygen to create oxides. Here we are having lithium oxide, and remember your more concept that you have to balance the equation. Okay, and here if we try to move further, you can see that even sodium is going to form an oxide, but look at the different types of oxides that are formed. Okay, so here I think I must mention to you, let me just move a little bit in front. I don't know whether I have passed it. I think it's a little bit behind here. You can see the types of oxides that are being formed. Now there is this reaction that I want to demonstrate to you. Okay, because somebody might not really appreciate the reactivity of the group 1 metals, but we can see that the metals here, so this M is just going to symbolize a group 1 metal, which can be lithium, sodium, potassium, going downwards like that. If you put a metal here, you react it with water, you will see that the group 1 metals are very reactive. They'll form metal oxides, which are just known as bases. Okay, and hydrogen gas is going to be produced. Okay, I am repeating again, those of you that are speaking, please make sure that your mic is off. You are disturbing us. Is it Samuel, Alice? You are disturbing us. Put your mic on mute. Okay, if you want to speak something, maybe raise up your hand, because on Zoom you can raise up your hand and I'll be able to see it so that you ask me a question. Now, I was mentioning to you and I was saying that the metals are going to form hydroxides, which are just bases. And also these metals, they can react with halogens. And we know that the halogens exist as diatomic molecules, which we can replace with X, with fluorine, chlorine, bromide, and iodine. And the reaction that you're going to have, you should be able to know these reactions. For example, I'll just give you an example of, let me pick, for example, sodium. So sodium, solid, plus, let me say chlorine, which exists as a diatomic molecule. So this is where the 2 comes from. It's going to give us, if you balance it like that, sodium, which is metal chloride. Okay, solid, like this. All of them have got a valence of 1. So this is the typical reaction, but are you able to see that you can use metals, react them with a halogen to produce a salt, which we are having here as sodium chloride. But I'm interested in this reaction, okay, in this reaction of having a metal and you're reacting it with water. And so I'm going to show you a simulation here. It's a lab of some kind, which I'm going to share with you on my screen right now. Okay, so you should be able to confirm with me if you're able to see. So are you able to see this lab which has just appeared?
Yes, yes, sir.
Okay, so let's come to this point. We look at calorimetry. Okay, you can see that it is loading. Now you can see what has appeared, right?
Yes, sir.
You are able to see this stand here and this balance here, right? Okay, so if you're able to see this, then okay, I am just confirming with you. Are you able to see everything that I'm showing you right now?
Yes, sir.
Okay, fine. So then let's go to our place, our place where we are having our substances. So one of the substances that I'm going to get for you is a coffee calorimeter. Put it here, and let's go on the metals. And on these metals, I'm going to pick 2 metals. Okay, now I don't know if people don't know how to follow instructions. You are speaking and I'm speaking. You're just creating chaos. So let me mute everyone. Okay, so I'm going to mute everyone. Somebody's asking me a question. Suvat, you're asking a question. Ask.
Sir,
Yes.
we are unable to see. It is just loading calorimetry. So we don't know where you are saying you are picking.
Okay.
Yeah.
Okay. Wait. So as you are speaking, please
We are unable to see.
switch off your mics. Some people want to be experimenting things, and yes, hence they'll be causing confusion. Okay, so let me redo it again. People are saying that it is just loading, right? So let me share this with you now. I'll share this with you. Are you able to see this?
Yes, sir. We're
Yes.
treating metals.
Yes.
Okay, so it's like I'll be, then when I open this metal, okay, so out of these metals I'm going to pick, let me look for lithium. Okay, so I'm going to pick lithium for you. So this is lithium metal, you've seen it, right? Okay, close it. I can only pick one metal at a time. So are we going to expect lithium to be very reactive according to our studies? I don't think so, right? Lithium won't be very reactive. Okay, so again, I feel that you won't be able to see, but I will pick my metals and I'll bring them here. Then I will share with you what I'm seeing. So let me do the share again. Unfortunately, this is what we have to undergo. So I'll share this with you again. Share. So you can now see what I'm seeing, right? Like we are back on the table with lithium here, with our coffee cup calorimeter here. Everybody can see this, right?
Yes, sir.
Fine. So what we're going to do is that we're going to add some water here because we are reacting a group 1 metal with water, right? So I will do it like this. So let me pick a beaker, for example, here. Pick a beaker, then add some water in this beaker. Okay. So I've added some water in this beaker. You know, there are some certain experiments that we cannot do, but with simulations where we are able to do them easily. So I'll get this water and I'll put it inside this coffee cup calorimeter. Okay. So I have added the water and the coffee cup calorimeter. Then I'll get lithium and put it inside there so that we see if the reaction is going to be very fast and very reactive, we should be able to see an explosion. If the reaction is not very reactive, then no explosion is going to be seen. That will show us the difference in the reactivity of these metals. So I'll get a metal and I'll put it inside there. You have seen what has happened, right?
Yes.
Yes, sir. We've seen it, sir.
Yes.
We've seen it.
Okay, so even if we are saying that group 1 metals are not very reactive. Lithium is very reactive. That's why when you're in the lab, you don't pick any group 1 metal when you're doing practicals with the children. Why? Because there will be an explosion. Okay, so maybe let's exit and redo the experiment again, but now maybe this time let's pick a group 2 metal and let's see if this thing is going to happen. Are we together? Okay, so I'm going to go back to the lab again and share. Okay, so you can see we are still in this lab. So there are different compartments on this lab. So I'm going to say, let's enter into this one. Sometimes when it's loading, it takes time, but when it has loaded, you'll be able to see it. So every time when it has loaded, please tell me that you can see what has appeared. So you can see this thing again, right? Okay.
You can see. We are
Okay,
now
fine.
entering the lab.
Okay, fine. So I don't know. I don't know those who are shouting. I don't. It's very difficult to tell people. Okay. So let me try to mute them. Yes. So I've muted everyone. If you want to ask me a question, just raise up your hand. I'll unmute you so that we don't get the disturbances of those that are shouting. Okay, so now let's go back in this place. Okay. I don't know if you are able to see where we are picking the chemicals. Are you able to see? It takes time to load, but others.
Though it's still loading for me. I don't know others. It's still loading for me. Where we are getting the chemicals.
Yeah, of course, even to me, it's still loading.
So it seems that at this stage for everyone, it's loading. Okay, fine. We can still select this and share it. So now you can see it, right? Where we're getting the chemicals.
Oh, yes, sir, we can see it now.
Yeah. So here again, we're going to get a coffee cup calorimeter. Unfortunately, this is a simulation. You have to start over again. Okay, so here, now we know that the group 1 metals are very reactive and with water, but inside what was formed there, and look at this, the reason why it exploded there is because the lithium that I picked, I don't know, are you able to see where I'm getting the metals?
Yes, sir.
Okay, so if you saw here the lithium where I picked, are you seeing that this lithium is a very big chunk? Okay.
Yes, sir.
Yeah, it's a very big chunk, so you need a very smaller chunk. A smaller one won't explode. Yeah. And if you go on YouTube, you'll be able to see some of these experiments, but this also just tells you. So if I'll pick magnesium, we know that magnesium is in group 2. So meaning that it won't be as reactive as the group 1 metals. Okay. And of course, we will not be able to see hopefully some explosion. But maybe let me pick a transition metal for that matter. So let me try to pick a transition metal. Maybe I come here. Let me pick copper, for example, because we know that transition metals are not very reactive. And so I'll pick copper here and I'll put it here. Okay. And I'll go back to where we are getting our, and then I'll go back to my table so that now I share it again so that you can see. So if I go back to my table, now you can see that we are on the table, right? So I'll get the coffee cup calorimeter and I'm going to get the copper there. Get a beaker, add some water inside there. Okay. Then I'll pour it inside the coffee cup calorimeter. Then I will put the metal inside there. Have you seen? Nothing has happened. No explosion, right?
Yes.
Yeah. So
yes, sir. Yes, sir.
So here we have just compared a group 1 metal and the transition metal, but we would have also compared it with magnesium. We would have seen that magnesium also won't give us an explosion. But all the group 1 elements are so reactive that they are explosive. Okay, but now imagine if lithium can be that explosive, a big chunk. How about francium? Then it's a bomb, ladies and gentlemen. Okay, so here we are doing 101 how to make bombs, right?
Yes, yes.
Okay, so let me now share let's go back to the lecture notes. So I think from the lecture notes, we've been able to see this reaction, this one. Okay, why? Because our
Yes.
simulations has allowed us at least to see how the metals are going to react with water. Okay, but you can also go and see. And you see that most of these metals are very reactive. That's why if you just keep lithium just like that, it's going to react with oxygen and create an oxide layer. So most of these are kept under oil. I think you know that. Okay, they're kept under oil because they're very reactive. So you have oil and you put them inside the oil so that they don't react with oxygen. Okay, so in terms of these reactions, the reaction of sodium with what, I think you've seen these practical questions. I think you can try them out. And here I should also be quick to mention to you, ladies and gentlemen, that some of the uses of the group 1 metals, for example, like lithium, they use it in what are known as lithium batteries. Now, lithium batteries are one of the strongest batteries that you can use. Others are even putting lithium batteries in phones so that the phone can last for a very long time. Then if you look at lithium carbonate, okay, it is used in what is known as porcelain enamel. Now, if I was to describe for you porcelain, you might not know what it is, but I know you know what it is. And so let me just show you what porcelain is. Okay. Have we ever seen these? You know, this is Tumashan that we usually buy. Okay. You've seen these, right? We have seen these before, where they're making those those teacups and so on and so forth. And those plates.
Oh yeah.
You know that, right? So there,
Yes, sir.
when they are making those, they put a thin layer of a mixture of ceramic and glass. Okay, and we call that a porcelain. Okay.
What does it mean?
I am from showing you right now. Have you ever seen these before?
Not really, but the other parts, yeah, I think, yeah.
You mean you have never seen, those, maybe let me just try to open a picture and make it a little bit.
We have seen it before, sir.
Look, this, you've never seen these type of cups
I've
before.
seen, but we have.
I've seen them, sir, before.
Yes, and
Okay.
and these
This
cups, they have a certain layer. It's like they have like a certain layer on top of them, so that if you drop them, that layers, they come out. If you've dropped it so many times, you see that they appear like this. So that layer that they layer this with is what we call as porcelain. Are we together? It's a mixture of, yes. Have you gotten it right? So in making porcelain,
Yes, sir.
yes, in making porcelain, let me just try to go back and share my slides with you. Okay, so I think all of you, as you can see, there's so much that we can do on an online lecture than what we can do on a board, right? Because now I can show you things so that I don't spend time so that I can't spend 95 minutes describing things when I can just show you. Okay, So here you find that lithium is also used in making this porcelain enamel, okay, in the manufacture of glasses and so on and so forth, okay. And it is also used as an air conditioning, a dehumidifier. You know, sometimes you find that in the air condition, let's say there's humid in the room. You know what humid is, like moist, like. So you want the air that is going to be coming out of the air conditioner not to be wet air, but or maybe not to be humid air. So you need a dehumidifier, something that removes the humid out of the air. And lithium chloride does that. Okay. So I think we are following. Yeah, this one's saying mute these that are making noise. I'm telling you, I'm also trying to mute them. Seems they're immune to being muted. Okay. Mute. Yes. Wait first. Okay, I think I've done it now. Okay, then let me just maybe try to move a little bit forward, metal by metal. So these notes are made in such a way that we need to familiarize ourselves metal by metal each. What are some of the uses? Of course, we will not talk about all of them on the periodic table, but the essential groups that we're supposed to, to talk about. If we look at sodium, because we are moving from lithium to sodium, what are some of the important uses of sodium and extra information that we can know? We know that so far I've already explained to you that sodium is obtained by the electrolysis of molten sodium chloride and not aqueous. So the keyword here is molten, and I gave you the reasons why. Okay, but also we can produce a sodium hydroxide by electrolysis of aqueous sodium chloride. Now, do you remember last time when I showed you how sodium hydroxide can be produced? If we are going to use the electrolysis of aqueous sodium chloride, what is going to happen is that here you have, for example, your positive electrode, and here you have your negative electrode. Let me try to pick another color. Okay, maybe pick this color. So then maybe here you have your voltmeter or battery, and inside there, let's say you have aqueous sodium chloride, meaning that you have sodium ions, you have chloride ions, you also have hydrogen ions plus and hydroxide ions. Now, when this circuit is complete, we know that the positive ions, sodium is less reduced, hydrogen is highly reduced, so it's the one that is going to go to the cathode here. Okay, and this is the anode. So sodium will go to the cathode first before hydrogen will go to the cathode first before sodium, and it will be produced here as hydrogen gas. Okay, then in this case you find that the chloride ions also, between the hydroxide ions and the chloride ions, the ones that will go to the anode faster are the hydroxide, the chloride ions, so that the chlorine is going to be produced as chlorine gas this side. So on the cathode, we are producing hydrogen gas. On the anode, we are producing chlorine gas. What remains are these ones that cannot move very fast. So in the solution now, you remain with sodium ions and hydroxide ions. So that now the sodium ions and the hydroxide ions will be in aqueous state. So this is the aqueous that you're seeing. but hydrogen would have been produced as hydrogen gas and the chlorine would have been produced as chlorine gas. Any questions so far? I think everybody is able to understand, even though I've muted everyone. Okay, but you can get that point in terms of the production of sodium hydroxide, that we can produce sodium hydroxide from the aqueous electrolysis of sodium chloride. But if we're going to use molten, then no sodium hydroxide is produced. We are only producing sodium solid and and chlorine gas. And it is also important that, of course, I think everybody knows that that the sodium ions are an essential ingredient in foods, because it brings about a electrolytic balance in our body. Our body must have a certain number of ions in our blood, so that of course we know that our blood is an electrolyte. Our body is able to conduct electricity. So for electrolytic balance, you need sodium. Those that are going to go into biology, I think you do a lot of understanding on this one, but all of us know that inside our body, we take in different types of ions, and sodium is one of them. Okay, then on sodium, I think we can also talk about some of the uses, like our day-to-day uses of sodium. We know that sodium exists as sodium hydrogen carbonate. Okay, others will just call it baking soda. Okay, and I think our colleagues, the ladies, they know very well. They've seen this one almost on a daily basis when doing the baking of cakes and so on and so forth. But there we are having sodium hydrogen carbonate, okay, where we are having the radical, the hydrogen carbonate radical with a valency of 1, and sodium group 1. So when you cross the valencies, this is the formula that you're going to have. Okay, and also there's what we call as sodium carbonate. This is a very, very important ingredient in the manufacture of glass. Okay, and it is often used as an industrial base. Okay, of course we know that in the industries, during different processes, they end up producing acids. Okay, and so in these acids, they require to be neutralized, and so sometimes sodium carbonate is used as a base for the for the neutral reactions that are required to neutralize the acids. I think I should also be quick to mention to you that sodium hydroxide, I think from what you are all able to see, it can be used as in the manufacture of household bleach. Okay, there are different types of household bleach that can be found on the market, but one of the ingredients that we find there is sodium. In what form? In form of sodium hydroxide. Okay, where now you are going to produce this bleach compound there. Okay, plus sodium chloride. So this combination is actually a household bleach. Okay, and this household bleach is what is going to be used in cleaning of drains and so on and so forth. I don't know if you have any questions before I try to conclude on the group 1 metals. But as we can all see, ladies and gentlemen, that if we look at the element like potassium, this one is also going to be essential in the electrolytic balance of the body. However, it is used mainly in the nervous system. And if you look at potassium, potassium is an important component in the fertilizers, because we know that in our fertilizers there are what are known as mineral nutrients and non-mineral nutrients. The non-mineral nutrients are carbon, hydrogen, and oxygen, and the plants often get these from let me say carbon dioxide in the air that we breathe out and water. Okay, so they are able to get their carbon from the carbon dioxide that we breathe out, and they're able to get their hydrogen from the water. However, they need the essential mineral elements, potassium, phosphorus, and nitrogen. And sometimes these are known as the NPK nutrients. And one of these mineral elements that are essential to the plant is potassium. And so potassium is this potassium oxide, when they are manufacturing fertilizers, it's going to be used very much. I should also mention to you that potassium oxide, of course, is also used in places like submarines for the removal of carbon dioxide and the production of oxygen. Because you know that in the submarine, I know we know what a submarine is. Okay, these are vessels that usually advanced nations use to navigate the sea. Okay, it's found under the sea, but you know that there are human beings inside this submarine who are supposed to breathe in oxygen and breathe out carbon dioxide. But the submarine is underwater, so meaning that they don't have any other source of oxygen, and the carbon dioxide that they are breathing in, they don't want it in high concentration within this submarine for them to continue breathing. So what processes then are they going to do to have more oxygen and less carbon dioxide? Okay, so what they're going to do is that this potassium oxide can be reacted with carbon dioxide so that we produce a potassium carbonate, which is a solid, and produce more oxygen. Are we together? So the oxygen, the concentrations of the carbon dioxide inside that submarine will be reduced using potassium oxide. As I'm about to unmute everyone and make a conclusion, are there any questions, ladies and gentlemen? The other things I think you are able to read for yourselves and see how I am explaining the stuff to you. I've made these notes in a very, very summarized way, and you're able to read. Any questions so far? I think I've unmuted everyone. Yes. Is it honest? At least, yes. If it's clean to speaking, I cannot hear anything. Maybe your network is bad. You can just type. Those whose network is better. Okay, yes, Nen.
So are you going to post the video on Moodle?
Yes. No, I'll not post this video on Moodle. I'll post it on WhatsApp. The recorded video. I'll post the link on WhatsApp.
Okay, thank you.
The YouTube link. Yeah.
Also, I've got a question.
Yes, ask.
What does KPN means?
KPN. K means potassium, P means phosphorus, N means nitrogen. These are the essential mineral elements that are used in plants. And whenever you're making a fertilizer, all fertilizers contain KPN. Other fertilizers are going to give you potassium, other fertilizers are going to give you phosphorus, others will give you nitrogen. I was concentrating on the need of potassium, that potassium oxide is important in the manufacture of fertilizers. I hope I've answered your question.
All right, sir.
Okay, so I think we are done, ladies and gentlemen. Have a good day, and we'll see how we're able to prepare the test so that people can write. If we want, then we'll see. I'll be able to advise. But we are settling for 6th. Okay. Yeah. So Zoom is going to just automatically switch off, but we can end our lecture just here.